Hello, David here, and welcome to a tutorial on behaviors used while modeling a new component in Visual Components. When following any tutorial, check the lesson on the Visual Components Academy, and if the Download Files option appears, you can download the example files. Using some of the most commonly used behaviors, we will model a turntable component which will guide the products from one conveyor to another. Our starting point will be a shape feeder, placing the products onto a single conveyor. In a component, behaviors perform different tasks. These tasks together define how the component functions, what the behavior or logic of the component is, and to which other components this component can be connected and how. Most of the behaviors are bound to a certain position in a component, but not to the actual geometry, rather to frame features in the component's feature tree. For example, the path behavior, which defines where the conveyor track is located in a component, does not rely on the visible geometry, but on the frame positions, located at the beginning and end of the geometry. And now resetting the simulation. To learn what the most common behaviors are and how to use them, let's first create a simple geometry for our turntable component, define some frames for it, and then add behaviors to the component to make it function in the same way as other simulation components in the eCatalog. We are in the Home tab, and using the PNP tool, let's first move the conveyor out of the way, since we don't need it right now. And then to create a new component, go to the Modeling tab and click New. This will create a new component at the world center. For now, the component is empty, as it does not have any geometry or behaviors. To quickly create the required geometry, select the feature tree root on the left, and then from Features, select Block, and change all block dimensions to 700 mm. When a block geometry is created, the location of the component's origin will be its front left bottom corner, which offsets the geometry from the center. And as it's common practice to keep the component origin at the center of the component's geometry on the floor level, we will move the block with -350 in both x and y directions using the coordinates, which will center the block relative to the component's origin. And next, let's create some frames. To add a frame, select the root from the feature tree on the left, then select Features and click Frame. Change the name of the frame to Center 1, and move the frame using the coordinates to the top of the block by changing the z-axis value to 700, the height of the box. If the new frame is not visible, enable frame visibility using frame types from the 3D World toolbar and toggle the visibility on. After the first frame is created, let's create 3 more frames. One for the input, one for the output to the side of the turntable, and a third one at the center, but with a different orientation. The orientation of these frames matters, because by default, the product's orientation is relative to the frame orientation, or for example, to the interface's orientation. So let's create the frames. We will copy the center frame by selecting the center 1 frame from the root on the left, right-click and select Copy, and selecting the root, right-click and select Paste. Then move the copy backwards, -350 on the x-axis, and rename it as In. Then selecting the root, right-click and paste the center frame we copied again, and move it sideways 350 in the y direction, and rename it as Out. And rotate it 90 degrees on the RZ rotational axis so that the x-axis, the direction of travel, is pointing outwards. and selecting the route once more, paste the center frame one more time, rename it as Center 2, and rotate it 90 degrees on the RZ rotational axis. And now we have our geometry done. And now let's add our first behaviors. First, we want to create two paths, or conveyors, for our turntable component. The first one will represent the incoming conveyor segment, while the other will represent the outgoing segment. The path behavior, whether one or two directional, so one-way path or two-way path, will simulate any mechanism for the product to travel between two positions in the component. These positions are defined with frames, as mentioned before. In addition to the physical location of the path between the frames, the path behavior will also have other parameters to define, such as the speed of the path, the capacity of the path, or any sensors present on that path segment. The first path will be path in. So from behaviors, let's create a one-directional, one-way path behavior for our component and rename it as path in. The next step is to define where the path is located. So using the path property, we will select frames for the path. In this case, the path starts from the in frame and ends at the center 1 frame. We will not change any other properties for now. The second one-way path will be from the center 2 frame to the out frame and will be renamed as path out. So again, from behaviors, create another one-way path behavior and rename it as path out. And again, using the path property, we will select frames center 2 to out. Next, with our block component selected, we need behaviors that enable our new component to communicate and connect with other components. These behaviors are called interfaces. Each interface has a location, again defined with a frame, and they can have different connection sections and fields, like different types of electric plugs. These sections define what kind of data is passed through the interface. In our example, we will later use the flow field to interface the flow of products between components. Other common types include signal and hierarchical connections between two components. But by using a one-to-many interface, connections can also be made between multiple components. In this example, from behaviors, let's add a one-to-one interface and rename it as interface in. This interface will be located at the beginning of the path in and will interface the flow of that path to the path of another component. So let's add a new section to this interface. Define that it is located at the section frame in frame position and add a flow field to specify that we want to pass a production flow through this interface to this path in container and its input port. Similarly, let's create an interface out interface. So from behaviors, add another one-to-one interface and rename it as interface out, which will be located at the end of the path out. Again, let's add a new section to this interface. Define that it is located at the section frame out frame position, and again we will add a flow field and the path out container. But this time we want to connect the output of path out to this interface, so we select the output port so it is an outgoing interface. As you can see, many behaviors have internal ports that can be used to connect behaviors to each other within the same component. In this case, we have a component with two conveyor paths. To test this component, let's connect the output port of path in to the input port of path out. So we have the output port of the path in selected, and using connection connected to the path out and its input port. So now we have an internal connection. Let's test the component by connecting it to two conveyors and the shape feeder. So then returning to the Home tab, we can see that the interfaces have appeared, indicated by the yellow triangles. And using the PNP tool, select the conveyor and connect it to the component. And to create a second conveyor, let's copy the conveyor using Ctrl+C and Ctrl+V on the keyboard. Then using PNP, connect the second conveyor to the outside of the component, and pressing play to run the simulation and setting the speed to 5, the products will move through the component. Okay, so the products move, but this is not a turntable yet. However, as dynamic components are always contained or owned by someone, in this example, and we can now pause the simulation, the dynamic components enter the component through an interface, visualized as a yellow or green arrow in the 3D world. That interface behavior is connected externally to another component. But in practice, the path connected to the interface is just connected to the output port of the path in another component. So the interface is just an intermediary. So the dynamic components move from one container to another through internal ports or external interfaces, but they are always owned by some container behavior. And now resetting the simulation, let's now create the turntable. In the Modeling tab, create a new link for this new component, which will create a new node for the component, which can move and rotate and contain its own behaviors that follow the node, or more precisely, the behaviors follow the frames in that node. From the link properties on the right, rename the node to table and modify its z-axis value to 700. Then to visualize the turntable, we will first create a cylinder, so from Features, select Cylinder, and add a height of 10 mm, a radius of 200 mm, and 6 sections. And then selecting the root of this new node on the left to create a frame, from Features select Frame, and name it as Process. This will be the position of the component container, and later the position of the process. Next, from Behaviors, let's create one more behavior called Component Container. This container is just a dynamic component container that holds any arrived components. So products from the path in will be transported to the input port of this component container, and from this container they will be transported to path out, again via the connected port. So let's change the internal ports in this component a little, expanding the component container on the left and selecting the input from its properties. The input will be path in's output. So the connection is path in and the port is output. And then selecting the output of this container here in the center will be connected to path out's input. So the connection is path out and the port is input. If we now run the simulation, the products will enter the container, but they will never leave, since nothing is instructing them to do so. So then resetting the simulation, to add simple logic or PLC to this component, let's add two more behaviors. So from Behaviors, select Transport Node, and then Process Executor. The Transport Node behavior is the location where products can be routed in and out using the Process Flow Editor. In this location, the Process Executor can be used to define in more detail what should happen when the product enters the component container that is linked to this transport node. The Process Executor is the brains of this component, like a PLC or some other logic in a real-life machine. An alternative way to control this component could be a Python script behavior, where the script would react to the component entering the container and make decisions such as processing time and to which port the product is transported. So in addition to these process flow related behaviors, we could also have a product creator behavior. This behavior could act as a feeder in a component. This feeder is connected to, for example, the path behavior's input port and will publish its properties to the component properties, from where we can select, for example, what product is created and moved to the conveyor and at what interval. Okay, so to connect the transport node, we need to define the visual position frame, so the process frame, and the same for the default product position frame and the default resource position frame, and also which component container this transport node is using as a logical container, so component container. And then selecting the process executor, we need to define where the process itself is located, so transport node. And now if we briefly visit the process tab and enable the process editor, we can see the transport node we just created is visualized. And if we click on it, an empty process executor that we also just created appears. Let's now create a new routine and then add simple logic into the process executor. Clicking on the green plus adds a new routine, and from statements add transport in, delay, and transport out statements. Now we will change the mode of both transport in and transport out to container mode. Selecting the transport in statement, change the source to from component container, and selecting the transport out statement, change the destination to component container. As the product is entering the process from the container path in this example, also let's select the delay statement and change the delay from 10 to 1 seconds. Now if we run the simulation, we can see that the process routine reacts to the arriving component. The process time in the form of a delay is executed, and the product is transported out to connected container. But there is still no movement in our turntable. So then resetting the simulation, to add some movement to the turntable node, we return to the modeling tab, select the table node, and change the joint type to rotational. However, we can see the selection is grayed out since the component is still connected to other components. So returning to the Home tab, using the PNP tool, we can move the component to disconnect it from the conveyors. And returning to the Modeling tab, some parameters and behaviors cannot be modified while a component is connected. So then selecting the table node once more and changing the joint type to rotational, which will display the node's axis properties and also provide the option to define which servo controller is handling this axis. From here we can add a new servo controller, and note that we could also have added the servo controller from the behaviors. This servo controller can now run the axis based on its properties defined in the axis itself, such as limitations, speed or acceleration. And the servo controller itself, this can be controlled depending on the case. So either from the Robot Program tab, a Python script, or by statements in the process executor, which we will utilize next. So returning to the Process tab and the Process Editor and opening the Process Executor panel, select the Transport In statement and add a Move Joint statement below it. And in this Move Joint statement, let's add our newly created servo controller and its single joint J1. and what the target value would be, it would be 90 degrees, and we turn with a motion time of 1 second. After the product leaves the container, so after transport out, we would like to return the position of the turntable, which we can do by copying the move joint statement. So right-clicking and select copy, or using Ctrl+C on the keyboard, and then paste it after the transport out by right-clicking and selecting paste, or using Ctrl+V on the keyboard. And set the target value of the copy to 0, and keep the motion time of 1 second. And if we now reconnect the component to the conveyors and test it by running the simulation, we now have a functional turntable. But it may still need some polish. So we can reset the simulation to continue. The first thing is that every container in the simulation has a logical capacity. So going to the Modeling tab and selecting the path-in behavior, we can see from its properties that its capacity is by default 900,000 plus, which means that if the product can physically fit on the path, it can enter through the port from the previous container, as long as the logical capacity of the container is not full. But with the capacity controller behavior, we can create one capacity limit for multiple containers. For example, in our case, the whole turntable should have only one component at a time. So let's add this capacity controller from the behaviors, change its capacity to 1, and assign it to both pathway behaviors. So both path-in and path-out behaviors, by adding it to their capacity blocks, and also to the capacity blocks of the component container behavior in the table node. Now, if we run the simulation, we can see that the behavior has changed. So now the product will pass and the other component will wait until it has the capacity to enter. Much better. And now resetting the simulation, we still have 2 more details to add. Running the simulation again, as you can see, and we change the simulation speed to 1, the turntable starts to return immediately when the product leaves the process container. So practically when the product enters the second path. What we should do is wait until the product has moved at least a little bit before we return the orientation of the turntable. To achieve this, we can add sensors to the pathway, and those sensors can send a signal to, for example, a process that waits before commanding the servo to return. So now resetting the simulation, to do this, first we need a signal. So selecting behaviors on the left, and from behaviors above, add a Boolean signal. For a simple pathway sensor, a Boolean signal should be enough. In more complex cases, for example, in communication between behaviors and a script, or between components, a string type signal is really common, and especially with Python scripting, the component signal is useful. And in addition to the signal, we need the sensor itself. In this case, from the behaviors, we will create a path sensor, which we will connect to the Boolean signal. From the properties of the path sensor, we need to define the location of the sensor by selecting a frame, center 2 in this case. And also the sensor behavior, now it triggers at leading edge and resets at trailing edge. We will set both of these to be trailing edge, meaning that when the product's geometry is about to leave the turntable, a trailing edge is detected, and the signal is sent when it passes the center 2 position, and then we trigger the Boolean signal. And the last thing to do is to add this sensor to the existing pathway, as the path sensors are always also associated with the pathway. So in this case, the path out should have a component path sensor. Now in the Process tab and the Process Editor, and opening the Process Executor panel, we can add one more statement to our process and reorganize the statements a little. Let's add a wait signal statement, and from its properties, change the signal that we want to wait for to be the Boolean signal, and we need to wait for a condition to be true value from that signal. And after we receive the signal that the product is about to leave, and we move the wait signal statement up above the move joint statement, and after that we can move the joint back. And we will also move the delay statement below the wait signal statement, so it runs after the signal detection, to allow a little bit more time for the product to leave the turntable before we return the orientation of the turntable for the next product. And now if we run the simulation, we should be able to view the correct behavior. So there is time for a product to leave, and then the turntable returns and the next product can enter. So now resetting the simulation, last but not least, most components should have statistics from which we can see the performance of the machine and the product flow through the machine. So in the Modeling tab, from Behaviors, we will add a statistics behavior to the component. This behavior has two types of values: flow statistics, which are different types of counters based on the product movements in a selected container, and a state model, where, for example, a process can change the active state of the whole component, and from those states, utilization can be calculated. To add the default states to the statistics behavior, use the Create Default States button. The last thing we need to do is to assign the behavior to a container, like path out. So from its properties, select Statistics, and to change the state of the component from the process itself with statements. So in the Process tab and the Process Editor, open the Process Executor panel, and selecting the Transport In statement, from Statements add a Set State statement to set the state of the machine. Then select Statistics and set the state as busy. Then using Ctrl+C and Ctrl+V on the keyboard, copy and paste the Set State statement and drag the copy to the beginning above the Transport In statement. And at the beginning the state is idle, and we can now close the Process Executor panel. And now from these two changes, returning to the Home tab and opening Statistics, we can create the basic statistical report for this component. For example, we can follow the component's utilization, or maybe the production rate of the component. And now, if we run the simulation and increase the simulation speed, we will start to collect statistical information such as the utilization of the machine and how many parts it has produced so far. And this concludes this tutorial, where we introduced the most common behaviors in components. Thank you for watching.